The act of composing music has been regarded as strictly a human activity for very long. However, due to advancements within the field of deep learning, this notion gets challenged. The topic of computers generating music on their own is interesting, and we wanted to delve deeper into it with our project. So we set out to create a model that generates harmonies given a melody. In order to create this model, we needed data to work from, and after deliberation, we landed on the JSB chorales dataset. The dataset consists of 382 different musical compositions made by the composer behind the initials Johann Sebastian Bach. The notes for the musical pieces are represented as the pitches for each SATB voice type, which includes soprano, alto, tenor, and bass. Within the dataset, these pitches are specified for each note of the songs by their equivalent MIDI pitch value. The pre-processing of the data included transforming it into one-hot encoding. One difficulty we also had to address with the pre-processing is making it possible to generate harmonies for different keys. To solve this, we transposed the data into every possible key while still remaining within the appropriate vocal ranges. This would also increase the dataset size from 382 pieces to 2,888 pieces. The soprano voice type is representative of the melody, which means that our model has to generate harmonies for the remaining 3 voice types. Let's take a closer look at how this was achieved.
Our model was largely inspired by sequence-to-sequence networks, which are most commonly employed in machine translation. We chose to work with a sec-to-sec structure, since creating harmony from a melody can, in a way, be seen as translating between 2 different musical languages. However, there is one thing that makes our case a little bit more complicated. When arranging harmonies, we have to translate to 3 different languages at once, and each translation affects both of the others. Our experiments with different architectures had a bit varying results. Eventually we arrived at this model. Simply put, a 3-part sec-to-sec structure using gated recurrent unit layers. The melody is encoded using an initial GRU, which is supposed to capture general characteristics of the input. The result is then sent into a 3-part pipeline consisting of 1 encoder and 1 decoder for each of the 3 harmonies before they are combined with a fully connected layer. This way, each harmony can have an encoder-decoder that is specialized for working with that specific harmony and look at different aspects of a melody, which is similar to how actual musical arrangement works. By then combining the outputs with a final shared fully connected layer, the model should, in theory, also learn how the melody and harmonies interact with each other. This architecture was powerful enough to overfit and recreate the chorals exactly, so we introduced regularization through dropout on the GRU layers and early stopping of the training when the validation loss stopped improving.
Let's listen to how our harmonies sound. First we have the classic Twinkle Twinkle Little Star. Now let's listen to another classic, Amazing Grace. It sounds quite good. What's interesting about these samples is the fact that it doesn't really resemble the works of Bach. This is because of the syncopations found in the generated compositions, that is, the offbeat notes that make the song sound funky. We suspect this is due to how the data was encoded. But now let's listen to Amazing Grace, but this time in another key. From this, we can hear that the model managed to generate harmonies despite the input melodies being played in different keys. This points to the model actually having learned what the core function of harmony is, instead of just looking at specific notes. The harmonies also respect the vocal ranges of the performers. The cause of this generality is, in all likelihood, the data augmentation strategy that we had, where all data was transposed to every possible key, as described earlier. You have now seen our model and the results from it. So to wrap up, our take-home message for you is that data augmentation is great. So if you ever find yourself stuck chasing better performance by creating more complex models, consider augmenting the data or changing how the data is encoded, since this is what made the biggest difference in terms of performance for us.